Hello and welcome to The Explainer. Today, we're going to dig into the secret history of machine learning. And you might be surprised to find out it's an idea that's way older than computers.
So to really get what machine learning is all about, we're not starting with silicon chips or, complex code. Nope. We're actually starting with a pretty wild story from over 300 years ago. It all comes down to this question. What on earth does 17th-century life insurance have to do with modern AI?
All right. Let's get into it. We're in the 1690s. The famous astronomer Edmund Halley, yep, the same guy with the comet, gets his hands on these simple records of births and deaths from a city in what's now Poland. And just by looking at this data, he spots a pattern. This lets him build the world's first ever life table, which basically predicted how long people would live. And get this. He used it to help the King of England figure out how to price annuities to fund a war.
And this is where it gets really interesting. The big idea Halley stumbled upon was, well, revolutionary. He realized he didn't need to know anything about the biology of aging or the physics of life and death. Not at all. All he needed was to find a pattern in what had already happened to predict what was going to happen. And that insight right there, that prediction requires no physics, no deep theory of why something happens, that's the absolute core principle driving machine learning even today.
So that idea of learning from past data brings us right to the doorstep of modern machine learning, and specifically to the core concept we're going to talk about first, something called supervised learning.
Supervised learning, at its heart, is really just learning from examples. Think about it like you're teaching a toddler with flashcards. You show a machine thousands, maybe millions of pictures that you've already labeled. This is a cat, this is not a cat. And after seeing enough examples, the machine starts to figure out the general rules, so it can spot a cat in a brand new photo it's never seen before.
But here's the catch, the central challenge of the whole thing. What we really want is for our model to be accurate out there in the real world. That's the population risk. But of course, we can't test it on every single possibility in the entire world. It's impossible. All we have is our small slice of data, our sample. So the whole game is to get the error rate on our sample data, the empirical risk, as low as possible, and just hope that it works well on all the new stuff it hasn't seen yet.
You know, one of the first, and I think one of the most elegant, algorithms designed to solve this exact problem was something called the perceptron, which was developed way back in the 1960s.
The logic behind the perceptron is it's beautifully simple. Just imagine you draw a random line on a graph to separate your cat data points from your not cat data points. Then you just pick one data point. Is it on the right side of the line? If yes, great, do nothing. If it's on the wrong side, well, you just nudge the line a tiny bit to help classify that specific point correctly. And then you just do it again and again, thousands of times. This basic process of just learning by correcting its own mistakes, which we now call the stochastic gradient method, is literally the engine that powers most modern AI. Okay, but what happens when a simple straight line just isn't enough? I mean, what if your data is arranged in a really tricky pattern that one line can't possibly separate? This exact problem, this limitation, is what led to the next huge breakthrough in the field.
So pretty quickly, the early AI researchers really hit a wall. They found that some patterns, like the famous XOR problem, are just impossible to solve with one straight line. Imagine you have 4 dots on a piece of paper, like the corners of a square. If the 2 dots on one diagonal are cats and the 2 on the other diagonal are not cats, well, go ahead, try to draw one single straight line that separates them. You can't. It was a fundamental roadblock.
But the solution they came up with? It's really ingenious. It's like, okay, if you can't draw the line on a flat 2D piece of paper, what if you could just lift some of the points up into a third dimension? By creating new, more complex features from our original data, we can essentially lift that data into a higher dimension. And suddenly, in that new 3D space, a simple flat plane, which is just a line in 3D, can separate the points perfectly. And this whole idea, the power of changing how you represent the data, that's really the story of how we got to modern AI. It started with these clever mathematical tricks, like adding polynomial features. Then it evolved into these super powerful kernel methods, which could kind of magically map data into insanely high dimensions. And now we have deep neural networks, which take this to the logical extreme. They learn their own complex, layered representations completely automatically, just from looking at the data. All right.
So now you've got these increasingly powerful models, but they were hungry. They needed fuel to run on, and maybe more importantly, they needed a common yardstick to measure progress. That all came together in the 1980s with what was basically a revolution in research, the benchmark dataset.
These standardized datasets, things like TIMIT for speech or the famous ImageNet for images, they were absolute game changers. For the first time, you had this common playground. Researchers all over the world could compete, head-to-head, testing their new algorithms on the exact same data. It created this incredible competitive environment that just turbocharged progress at a rate no one had ever seen before.
But this incredible, super fast progress came with a flaw, a really big one. Because the data that we use as fuel for our models, well, it's never a perfect mirror of the real world. It's always just a snapshot. And a lot of the time, it's a pretty biased and skewed one.
Let's just take a look at that influential TIMIT speech dataset. The demographic breakdown is, well, it's stark. The data came from speakers who were over 91% white and mostly male. So what does that mean? It means the entire foundation for early speech recognition systems was built on biased data. It means we were creating systems that were, from day one, just inherently better at understanding one type of person than another.
And look, this isn't just some historical problem we've solved. It has very serious, very modern consequences. You can see it in landmark research showing how facial recognition software performs terribly on darker-skinned women, but works almost perfectly on lighter-skinned men. You see it in the heated debates around tools like Compass, a risk score used in the U.S. justice system that showed dramatically different error rates for black and white defendants. The takeaway is always the same. The biases in our data become the biases in our AI's decision.
And that leads us to our final point, which is maybe the deepest and most profound limit of all for machine learning. What happens when our predictions actually start to change the very reality they're supposed to be observing?
To get our heads around this, let's go all the way back to the beginning, back to King William III. In 1696, his government, still needing cash, came up with a tax based on a pretty clever prediction. They figured, hey, the number of windows a house has is a really good predictor of how wealthy the owner is. Seemed like a solid, fair way to do it. But the tax had a very peculiar side effect. A consequence nobody saw coming. People just started bricking up their windows to avoid the tax. So the prediction itself, once it was acted on, completely changed the system. The strong link between windows and wealth started to fall apart.
And this story reveals a really fundamental feedback loop. Our predictions aren't just passive observations of the world. No, they are active agents of change. They cause people to react, to adapt, to change their behavior, and those changes can completely break the original pattern the prediction was based on.
You know, the critic Ursula Franklin put it perfectly. She said that context is not a passive medium, but a dynamic counterpart. We constantly underestimate how people and society will respond to the predictions and technologies we unleash. The world pushes back.
And that leaves us with the ultimate question. From Edmund Halley's simple life tables all the way to today's massive neural networks, just recognizing patterns has taken us an incredibly long way. But as our predictions become more and more woven into the fabric of society, they will inevitably change that society. So what comes next? What do we do when the patterns of the past are no longer a reliable map for the future that our predictions are actively helping to create?
All right, that's what we've got for this explainer. Thanks so much for diving in with us.